So this is just the PowerPoint that the publisher has for chapter 6 in the Fauber. And so I'm just going to use it because I figure why recreate the wheel, you know? So we're going to reference the Fauber a couple of times with some of the images, and actually I might turn the lights up and down so that you can see your images in your book, because they don't project real well here for you to be able to actually see what they're wanting you to see in them. So let me go ahead and get to mine. Right. So we're going to look at go back to MA, time, math, KVP. I'm not going to read all of these. We're going to look at all of the things that we have, all of the formulas that we've learned so far, and how each, what individual things that we change, how those affect our 4 big quality factors of receptor exposure, contrast, distortion, and spatial resolution, because that'll also be part of the practical. So MA, the relationships are very, very important that you know what type of relationship these different factors have to receptor exposure or contrast, magnification or size distortion, and spatial resolution. So MA, directly proportional to radiation quantity exiting the X-ray tube, inversely related to exposure time to maintain exposure to the image receptor. We're going to look at that one in just a minute. Exposure time. So MA, exposure time, and a combination of those mass have the same relationships to not only the quantity of photons that are exiting the tube, but also to image receptor exposure. So again, exposure time has a directly proportional relationship to quantity, inversely related to MA to maintain exposure to the IR. Kilovoltage, KVP, directly related to quantity, but not proportional. So we never talked about doubling KVP will double receptor exposure. It's not a proportional relationship, but it is direct. Come on in. Okay. It is inversely related to radiographic contrast. So more specifically, subject contrast is probably better to put in there than radiographic contrast, because we know that radiographic contrast or display contrast is now really controlled by the computer and the algorithms, the processing parameters, the post-processing. You can make the contrast pretty much look like whatever you want it to. So a better word right here, I would say, would be subject contrast, because that would be true. Meaning if KVP goes up, then subject contrast is going to go down, inverse. So MA and exposure time are combined, MAS, have a direct proportional relationship. I didn't do this. This is the publisher leaving out words. Y'all see that? It's a directly proportional relationship to the quantity of radiation reaching the IR, which just simply means that if you double any one of those or the combination total, then it's going to double the amount of quantity that's going to reach the IR. And this picture is also from your Fauber book. That one is on. I'm not too concerned about these because you can see them pretty well. It's the radiograph pictures that don't show up real well here. So this is just showing that if you have more mass being directed at the patient, it just makes sense that you're going to have more exposure to the IR that actually interacts with the IR. So this is an example of what law. These right here. Oh, I'm sorry, it's not really. This is more of increasing or decreasing the MA results in a proportional change in mass. I'm sorry, I'm jumping the gun. So this is just saying, do you notice what is happening here as you increase MA? What's happening to your mass? So every time we double MA, we double mass. Okay. Here we're doubling time. So if we double the time, then it's also going to double the mass. So increasing or decreasing the exposure time results in a proportional change in mass. And we've already talked about that a great deal. This one is where I thought we were. So this one is maintaining mass. So this would be an example of what law? Reciprocity. Yes, reciprocity law. Meaning that there can be multiple combinations of MA and time that equal the same mass. So here, they're just calling it maintaining mass. So it just means that if you're trying to keep one particular mass value, you can adjust the MA and the time and keep that same mass value. And so what that statement was saying earlier, let's get back to it real quick. This one, where it says inversely related to MA to maintain exposure to the IR. That means if your goal is to keep the same mass, then if you increase your MA, what has to happen to your time? It has to go down, or vice versa. So if you increase one or the other, then the other one has to do the opposite if your goal is to keep the same mass value. So that's what this statement is saying. MA and exposure time have an inverse proportional relationship when maintaining mass. So if you double MA, you would half the time to keep the same mass. That's all that's saying. Okay. Changing kV. Kilovoltage affects, we know that it affects both quality and quantity. Okay. Remember, we said it actually has more of an effect on quantity than mass does, right? Because it only takes how much of a change in kVp to either double or half receptor exposure? 15%. How much of a change in mass does it take to either double or half receptor exposure?
Like 2 times.
Yeah, 2 times or 100%. Like we have to increase the mass 100% or use twice the mass to get the same effect that the change of 15 kVp gives us. So kV also affects through affecting quality. It's through the penetration of the beam. So the X-ray beam penetration and absorption in anatomic tissues. So increasing the kVp increases the penetration of the beam and decreases absorption, which just makes sense. If the beam is more penetrating, then that means that it is going to have a better chance to just make it through the body part instead of being absorbed in the body. Decreasing kVp decreases the penetration and increases absorption. Subject contrast, increasing the kVp decreases the subject contrast. So think about the Y. Okay, so as we increase kVp, because of what's being stated on this slide, it means that the penetrating ability of the beam is increasing. So as you increase that kVp, the part is going to be more uniformly penetrated, which means the brightness levels are going to be closer together. So there's going to be less difference in them, which means lower contrast. When there's little difference between the brightness levels, that means the contrast is low, right? If there's a whole lot of difference between the brightness levels, think about your black and white, like totally black, totally white. That would be the highest contrast that you could have. So the opposite holds true. Decreasing the kVp increases the subject contrast, because when you decrease the kVp, then there's going to be more photons that are absorbed in the body instead of making it through. So you're going to have more of that black and white that you don't get with the really high KVPs. And y'all stop me at any point that you have a question. Again, I know this is a lot of review, but you'll be glad when you get to that practical. So, so for example, if you can tell on this one, so this is showing you that lower contrast. Do y'all see that when I jump between them? So in this one, it's more grays. In this one, it's more what? Black and white. The blacks are blacker, the whites are whiter. And so this is just showing you that with higher KVP, that the part is going to be more uniformly penetrated. See how there's there's more photons that make it through, as opposed to here with lower KVP. These brightness levels, there would be a lot more difference between them than there would be on the slide before. So the blacks are blacker, the whites are whiter. So that would be higher contrast there. So when we look at image receptor exposure, which has been the whole goal through, everything that we've done as far as our in the lab, we're trying to maintain receptor exposure when we make these changes. So to increase exposure to the IR, increases in MA, time, or KVP, all of those things, when you increase them, increase image receptor exposure. Decreases in MA exposure time or KVP, decrease receptor exposure. To maintain exposure to the IR, if you increase MA, then you would decrease time. That is reciprocity law formula, meaning there's multiple combinations that can give you the same mass. If you increase time, that proportionally and decrease MA, that again will give you the same mass, so it would give you the same image receptor exposure. And then if you increase KVP 15%, then we would have to do what to the mass to compensate? If we're trying to maintain receptor exposure, we would cut the mass in half. Or the opposite, if we decrease KVP, then we need to increase the mass by 2 times or by 100%. Any questions so far? I know all this should be very familiar to you. So one thing we haven't gotten into the digital concepts a whole lot yet. I know we had that intro at the end of last semester, but in just a few weeks, we're going to be really getting into this digital stuff. Digital image receptors have a wide dynamic range. So I know you don't really know what that term means. It just means that your digital receptors have a wider range that gives you an appropriate patient dose and a good quality image as compared to film. Okay, so with film, it was much more narrow. So in other words, with film, you had to be much closer with your techniques to have a quality image than you do with digital. I'm sorry, actually, dynamic range, that is exposure latitude is what I actually gave you the definition for. Dynamic range just means any response to radiation at all. So with digital, the response that those receptors have is much greater than film still. With film, there was a amount of exposure that you really didn't see a response on film until you got to a certain amount of exposure. With digital, you pretty much immediately start to get a response. And I'm doing like this because we used to have what we called a characteristic curve with film. And if I had a marker, I would show you. I can show you. We'll get into that in a few weeks when we're talking about digital stuff. So don't worry too much about these statements yet because we really haven't had them in detail. The other thing it says is image brightness is not dependent on mass and KVP. and image contrast is not dependent on KVP. Again, this goes into the digital processing that's involved now. So don't worry too much about this slide. We're going to get into that a whole lot more in a few weeks. I will say, let's see what this says. So with too much mass and or KVP, the computer processing will adjust image brightness and contrast, but the patient's overexposed. So we've already seen this in the lab, where even if our EXI comes up really high, the image looks fine, right? And so the only way we would know that really we use too much, it wouldn't be a visual cue that we get from the image itself. It's going to be in that EXI number or that S value or EI or whatever exposure indicator your system uses. With too little mass and or KVP, the computer processing will still try to adjust the brightness and contrast, but you're going to have quantum noise visible. And so we've also seen this, where when we don't use enough technical factors, we begin to see that grainy salt and pepper look in the image, and that is quantum noise. I think we might have talked about this, or is that, I can't remember if that was here or the seniors, but using higher KVP and lower mass values. Did we talk about that last week, maybe with grids? Okay, maybe I'm thinking about the seniors. Using higher KVP and lower mass values is recommended in digital imaging because the computer primarily controls image brightness and contrast. So what this was saying is when we went from film to digital, that really across the board, we could increase the KVP about 15%, and that would allow us to cut the mass values in half, which would save patient dose, because with digital imaging, the KVP, it's important, but it's not as important in the displayed image as it was with film. So that's where you get into talking about how with film you could see subject contrast in the film itself, as opposed to all these processing parameters and all that we have. So this is on page 141 of your Fauber book. If you can see this one pretty well though, can't you? So this is just saying that if there's not enough, generally it's mass we're talking about. If there's not enough mass, then the brightness pretty much looks the same, right? When we talk about image brightness, that's how much light is coming through the computer screen at a certain area. So the image brightness pretty much looks the same, but what do you notice in one of the images? Which image has something in it that we don't want?
Noise in B.
Yes, noise in B. There's a lot of noise in there. Y'all see it? And if you look at your books, you can see all of this graininess in this image that we don't see here. This one is so nice. And do you see how that noise obscures some of these lines and things that may be important in the image? So that's why we want to be sure that we are not only checking our EXI numbers, but that we're also checking the image itself for noise. So this one is from page 144 in your book. So this is the one that I wasn't for sure if you'd be able to tell from up there or not. So on this one, let me see if they tell the KVPs that they used. So the first image was done using 70 KVP and 2 mass. The second image was done using 50 KVP, 2 mass, resulting in higher subject contrast, and the computer adjusted to maintain brightness, but we have an issue with noise. So what they did there was they dropped the KVP to 50 and didn't adjust the mass, so you have noise in this image. Also, 50 KVP is not enough for a knee. That's not going to penetrate well enough. And then in the C, it says the image was produced at 93 KVP and 2 mass, resulting in lower subject contrast, and the computer adjusted to maintain brightness, but the patient exposure is increased. So what it's saying is in this one, they used, did I say 93? 93. Again, that's way too much for a knee, but it was for, purposes of showing you what happens. Do you see the main thing that I want you to see from this, and that we'll talk about again in a few weeks, is the computer is doing what? Trying to do what? Correct it. Make them all look the same, right? Trying to make the brightness look the same across all three of those images. And it pretty much does that. It's just a difference in the amount of noise that we see and the contrast in this case where, I don't know if you guys can see it or not, but the contrast is definitely lower. The subject contrast is definitely lower in this one because that part is really well uniformly penetrated. So this one, if you look especially around some of the edges and all, it's a little bit higher contrast. So now we have actually looked at all of these things as of the end of last week when we finished grids. So we're going to talk about secondary factors. So we know that our primary exposure factors are KVP, MA, time, and SID. That's our 4 primary exposure factors, or you can say combination of MA and time for mass. Now, these are some secondary things that we have already discussed. So let's look at them individually here. So the size of the focal spot affects unsharpness and spatial resolution recorded in the image. Does focal spot size affect receptor exposure? No. Does focal spot size, that's always tricky to say, affect subject contrast? No. Does it affect distortion? Size distortion? No. Because remember that last practical from last semester? Some of y'all got the case that said change the factor that only affects spatial resolution. Who had that one? Do y'all even remember? When you had to change, all you had to change was focal spot because focal spot only affected spatial resolution. So it doesn't affect the other 3. Increasing the focal spot size, meaning using a larger filament, unsharpness increases, therefore spatial resolution would decrease. Because remember, if unsharpness goes up, then spatial resolution goes down. And then the opposite holds true. If you decrease the focal spot or use a small or smaller filament, then it decreases unsharpness and it would increase spatial resolution. And this is just an image to remind you of what's happening there. Remember that the focal spot is not a point source, meaning there's not just one spot that the photons are created. They're created across the size of the target. So you can see that this size is bigger than this size of focal spot. So it's depends on where the photon is created on that target. That's why you get a difference in the unsharpness and therefore the spatial resolution on the image. And this is just to show you the difference in the amount of unsharpness. This is supposed to represent unsharpness here in the image. And it's smaller with the smaller focal spot. SID. Okay, so now we're talking about inverse square law, exposure maintenance formula. So SID and radiation intensity are inversely related. Okay, so earlier we said that of the 4, that if we increase MA, time, or KVP, it does what to receptor exposure? If we increase any of those 3, it increases it. So what happens to receptor exposure when we increase SID? It goes down. So it's different, right? So it's the only one of those 4 that if you increase it, receptor exposure actually goes down because of the change in distance that changes intensity, right? So here we say inverse square law, increasing the SID will decrease the intensity of radiation reaching the IR, or decreasing the SID will increase the intensity of radiation reaching the IR. And it's by a factor of the square of the distance, right? So it's inversely proportional to the square of the distance. So you can't forget to square the distance in these formulas. SID also affects size distortion or magnification and recorded detail slash spatial resolution. Increasing the SID is going to decrease magnification, but make spatial resolution better. So again, if you then start to get all convoluted, think back to why do we do a chest x-ray at 72 inches? It's to decrease magnification of the heart and to give us better spatial resolution. So if we could do everything at 72 inches, that would be good, but we can't physically do that over the table. Y'all saw that in just doing the obliques of the C-spine. We can't get 72 inches over the table. So that's why they standardized two distances and said, okay, if you're using the upright bucky, then we're going to use 72 inches for chest and things like lateral C-spines. Again, it's not wrong to use, say, if you see your text using 72 inches on an upright abdomen, it's not wrong. They're doing that for a reason. It actually will decrease magnification, right? So there's a better chance that you're going to be able to fit the patient on there better at 72 inches than 40. Does everybody follow? But what do you have to do to that technique, your mass value, when you use 72 inches? You have to increase it. So it's really a trade-off. You say, well, if I can get the patient on one image at 72 inches, as opposed to bringing it into 40 and having to do two, then it may be better. If your patient is really large and you have to do two images anyway, so it may be, it may be better to do that at 72 inches. You just have to, it's very situational. We talked about that. All right, so here's the formula. Changing the SID requires a change in mass to maintaining consistent radiation exposure to the IR. So this is exposure maintenance formula. So what kind of relationship is this? Direct, because it's saying if your distance goes up, then your mass has to go up. If your distance goes down, then your mass can go down. So it's direct. You can say, you can use mass 1 over mass 2, or you can say new over old. In this case, it would be old over new, old over new. It doesn't matter as long as you keep them in a direct relationship. And so this is just another picture, a visual to help you see the difference in intensity at 20 inches. You see how much more intense. It's the same amount. I think Cody is the one that actually said this back when we were talking about this. It's the same amount of photons. It's just that as you increase the distance, the beam is diverging out. So per unit of area, there's fewer. Does that make sense? And then this is showing you the difference in SIDs and how that affects size distortion or magnification. So with greater SID, you have less size distortion or magnification, and therefore better spatial resolution with higher SIDs. OID is the distance between the part and the IR, and that does affect the intensity reaching the IR, but only with what? When we talk about the first two of these, it's really only with what that we learned at the end of grids when we did the
air gap.
Air gap. If this is only true, so the amount of intensity reaching the IR, which then also affects the amount of scatter reaching the IR, is really only if you're talking about an air gap OID, meaning you have at least 6 to 10 inches of OID. If you just have an inch of OID, that's not significant enough to really see a difference in the amount of receptor exposure and scatter reaching the IR, therefore it affecting contrast. So we're talking about air gaps when we talk about those first two. But we do know that OID does definitely affect magnification and spatial resolution. OID has the greatest effect on magnification. So when we did those activities in the lab, remember it only took like 3 inches of OID to see a pretty significant change in size distortion. And then when we changed our SID, we had to change it a lot to see a difference. So magnification has a greater effect. OID has a greater effect on magnification than does SID, but they both do affect it. So air gap is going to decrease the intensity of radiation and scatter reaching the IR. The thought behind that is that with the greater distance between your part and your IR, there's a better chance that the scatter is just going to miss the IR. Okay, it's a better chance. It's just not going to make it there. So if that happens, then even though scatter is unwanted, it is a part of receptor exposure. So it would decrease receptor exposure. And anytime there's less scatter on an image, what does that do to contrast?
It increases.
It increases it. It improves it. It makes it better because you no longer have that scatter fog on your image. Decreasing the OID also increases, I'm saying, wait a minute. Oh yeah, no, yes. Oh my gosh. I'm reading this last one is saying increasing. Decreasing the OID does decrease magnification and it does improve spatial resolution. Sorry. And this again is just showing you the air gap. The thought that if there's a bigger air gap, then maybe some of the scatter misses the IR. And here is just showing you that the greater the OID you have, the more magnification that you have in the image. So that's why we always say that it's very important to get the part as close to the IR as possible. Magnification factor we had to think about last semester, make sure my time is good here. So magnification factor you can figure out as either SID over SOD or image over object. And this is just they've just rewritten that. So again, you figure out SOD by subtracting OID from SID. This one again is just a review of the distances and magnification factor. So you can see that SID is made up of SOD plus OID. Central ray alignment, shape distortion of the anatomic area of interest can occur from inaccurate central ray alignment of the X-ray tube, the part being radiographed, or the IR. So there is an ideal relationship generally between those three things, where the central ray is perpendicular to the part and to the IR, and the part is parallel to the IR. So part parallel to IR, central ray perpendicular to both. That's ideal, generally. Any misalignment of those three things can alter the shape of the part being recorded on the IR. So that is important that we give an accurate representation of the part. This also is in your book on page 156. Okay, so this is just showing you in the first one, ideal, the part being parallel to the IR and the central ray being perpendicular to both. This is showing you that you can get, this would be elongation here because the IR is tilted. This one also would be elongation because the central ray is angled against the part. this one would be what? What's this one called? Where the part is not parallel. Yes, foreshortening. So this one is foreshortening here. Grids. Now, I'm not going to spend a whole lot of time on this because we literally just had this last week. So it doesn't change the amount of scatter that is produced in the patient. It changes the amount of scatter that reaches the IR. So it improves contrast. The grid conversion formula, you do have to still remember it. So if we go from using no grid to using a grid, do we need more or less mass? More. So that's a direct relationship. As grid ratio goes up, mass has to go up to compensate for that loss that we get from the scatter no longer being there, but also part of the primary, which would be called grid cutoff. When we lose part of our primary beam, that's called grid cutoff. Y'all should know those factors. This one is on page 159, and you can tell there, the first one was done without a grid. I don't know if y'all can see, but that's pretty low contrast there. The second one is with the grid, but no adjustment in the mass. So I don't know. I can sort of see the noise along the edge right here in the book. I could turn up the lights a little. And then here they actually did adjust the mass to compensate. So you no longer have that bit of noise there that you have when you forget to increase your mass when you're using a grid. Beam restriction. So a larger field size, meaning decreasing collimation. And I know that seems crazy, but always think about it this way. If you collimate more, what we consider more, then that means you are doing what to your field size? Making it smaller. So if you are decreasing collimation or collimating less, then that means you have a larger field size. A couple of y'all missed that on the test. So we need to make sure everybody understands that. Larger field size increases the amount of tissue irradiated, causing more scatter radiation to be produced and increasing the amount of radiation reaching the IR. So more matter, more scatter. And that always lowers contrast. A smaller field size, meaning we're increasing collimation, we're collimating more. That means we have a more narrow or smaller field size, which means less matter, less scatter. So we have to increase our mass to compensate for that loss. Even though it's unwanted, it's still a part of it. Now, the only one of these that we really have not talked about is this generator output thing. So it's going to be real simple what I'm going to tell you right now, because we're going to talk more about this in a few weeks when we get to QC, and then Ethan's really going to cover it a lot more in your physics class. I don't think it's in protection. I think it may be, I don't know. But anyway, so let's talk about generators. When we talk about the equipment, we're talking about the generators of the equipment. So generators with more efficient output, such as 3-phase units or high frequency, require lower exposure technique settings to produce an image comparable to those of a single phase unit. Let me see if we have. So what that's saying is, very rarely are you guys going to work with single phase equipment anymore. Dental still does, because they can get by with that because teeth are very small. They don't have to worry about huge amounts of radiation being output. Maybe if you go to work at a very small office, they might still have some single phase equipment out there, but it's going to be rare. Okay. So what this is saying is your 3-phase or even your high frequency generators are going to be much more efficient. Okay, and it goes back to the waveform, right? Have y'all had anything about that in protection yet? About how x-rays are produced in waves and the voltage dropping to below 0 and all that stuff? Okay, well, we're going to talk about that in a few weeks. So for right now, all I want y'all to know is, And that's on it's on that little sheet I gave you with the formulas. It takes twice as much mass when you are using a single phase piece of equipment than it does with a 3-phase or a high frequency generator. The high frequency or 3-phase are just more efficient. One way you can think of it is this, and it's not exactly right, but it might help you learn the concept. That 3-phase can do more with that one mass value that you have than the single phase can. Okay, that's all you need to remember. So with single phase, you have to use twice as much mass as you do on a 3-phase or high frequency. Or you can say it the opposite. If you're using a 3-phase or high frequency, you can use half the mass that you would use on a single phase. That's all you have to know about that right now. Okay, because we are going to do some problems in the lab today. But of course, we can't do this on a practical because we don't have any single phase equipment. So it's not going to be anything you're going to have to do on the practical, but you do just need to understand the math there. Filtration. How are we doing on time? Okay. Again, we went through filtration just a few weeks ago. Small variations in the amount of tube filtration should not have any effect on radiographic quality, meaning just little amounts of filtration. You probably won't really need to do anything to your technical factors. There's no kind of formula or anything like that. X-ray tubes that have excessive or insufficient filtration may begin to affect image quality. So we're going to talk more about that when we do QC in a few weeks. Now, compensating filtration are those filters that you either place on the patient or you put it, like attach it to the collimator face. So it might be a wedge, it might be a stair step. When you think about things like leg length studies, where we're talking about going from the hip down to the ankle, there's a big difference, right, between my little skinny ankle and big old hip, right? So there's a lot of difference. So we can use those step wedge types of filtration to just even that out. Usually it does require a little bit of an increase. In other words, you could use the mass that you need to use for the hip, and it's going to be fine for the ankle because of the added filtration in the compensating filter. So, and a couple of y'all missed this question on the test. If you are doing a foot, all right, you're doing a foot and you have the wedge filter, you know, the one that starts big and goes down like this. Would you want the thicker end to be over the toes or the part closest to the ankle? The toes. Because the point is, what we're trying to do is even that thickness out. So it would not do us any good to put the thicker end over the thickest part. We wouldn't want to do that. Then that just makes it that much more of a difference between the toes and the proximal part of the foot. Does that make sense? Okay. Body habitus, meaning if the patient's hypersthenic, sthenic, hyposthenic, or asthenic, does affect how you change your technical factors. Part thickness also does. That affects beam attenuation, exposure reaching the IR, scatter that's produced, image contrast. So the part thickness affects all of those things. Patient thickness, page 163. Let's look real quick and see what these are. This is the one that I was afraid you wouldn't really be able to see on the screen, but it actually doesn't look too bad up there. So A is the good quality hip that we saw actually earlier. That one's good, done at the correct technical factors. This B is the image created with added thickness with no mass adjustment. So just like we learned last week, and hopefully that you got when you did your homework, the exposure techniques assessment thing, if the part gets thicker, what do you have to do to the mass? Go up or down? Gotta go up, right? So 4 to 5 difference in part thickness, you would change your mass by a factor of what? 2. Yeah, so they didn't do that on this one, and you can see the noise in it. And then on the last one, they the part got thicker and they did increase the mass. So if you're looking, where'd my mouse go? This one, the EXI should be good. It should be close to, if we're doing ours, 250. This one is going to be low. It's going to indicate underexposure because the part got thicker and we didn't change the mass. This one should be close to A. So we should say that if we increase our mass with that increase in part thickness, then our EXI should be pretty close together because we should maintain receptor exposure. Oh, that was a lot, right? Okay, so at this point, I'm going to stop the recording because